Hi there. So I had a relatively sensible talk, which was about my experience from moving Java to Clojure, OO to functional. And I think there was a slight difficulty in the sense that we had a really good talk about that from Stefan yesterday, and a lot of things I was going to say I kind of agree with him. So I had to think, well, was it so hot that your memory of that talk would have evaporated and I should just play 003 and just give the same talk again today? Or, should I go and try and write a new talk last night that would be slightly different? And, Euroclosure, you're my people, right? So I thought, I'm going to stay up all night. I'm going to write a talk which I won't really understand, won't remember, and then deliver it very, very quickly, okay? So in these circumstances, it's really important to look at what you're passionate about and what you know about and what you think will be engaging for people. So here it is, okay? I don't know a lot about Clojure, but Euroclosure, with this, I will fight you and I will win. Well. But I won't win with the mark, max. Okay, we're almost there. So social media is really important, so I'm not suggesting that you post this to Facebook, Twitter, and LinkedIn. Anyone will do. I think this kind of summarizes what we're going to be doing. So my first thing is dot strings are useless. They're so useless you may not have heard of them. They're kind of like a pity fuck language feature. They didn't work in Python, and so they've got a second chance to not work in Clojure. Let's have a look at an example. I totally didn't understand how apply worked or how I should use it or whether it was valid until I read this, this one-liner, which is really unhelpful. But I don't just have to go to the core of the language to find examples of dot strings that aren't useful. I can just make them up. Quite often we have things like this where it's an afterthought. It's like, oh yeah, should I have to add a doc string? Well, it does stuff, whatever. And then you get the opposite problem where it's, you spend so much time writing the doc string, you actually forget to implement the code. So we've seen some logic language things, predicate selectors. These statements, if they're all true, then doc strings are a good idea. So you can get what your favorite query predicate language and find out whether they're actually a good idea. So what might be better? Well, there's clear code, first of all. I'll talk a bit more about that later. But, documentations are also a great idea for documenting code. We have some great stuff like Clojure docs, where you can talk, you can add examples, you can discuss things back and forth. GitHub has wikis where you can describe your project. So you could just add a URL where you describe the function, and then people can come and add documentation if you forget or it's not clear. Okay, another thing that's pretty pointless is private. It may seem a great idea, and there's maybe really valid use cases, but I think this code summarizes basically how it's really used, which is, I have my mad, embarrassing first wife in the attic, but let's pretend she doesn't exist, and then I'll expose a public method to you, and, you can burn down my house, and if she dies, it's all okay. It's all hidden, right? We're all good. So the issue with private is that functional functions don't need to be hidden, nor immutable data. And the interesting thing is that private probably doesn't work how you expect. We're in a dynamic reflective language, and private isn't quite the same as like private in a strong encapsulation guaranteed language from OO. Okay, so there is a case. A lot of people say but how do I reduce the surface area of my API, which I'm not sure is really the purpose of a namespace, but I think what you should do at this moment is I'd like you to pat the person next to you on the back. That's all of you, not just those guys and those guys? Yeah, okay. I guess it was kind of like, it came in, what's that reducer thing, it kind of all fine at the end. So the thing is, you're probably doing namespace aliasing wrong, but the guy next to you is probably doing it right, because overall, I think we're kind of getting it correct here. We have some really good examples from libraries about how to namespace things out. And this Second example here, down here, is maybe how we can hide some of the things we're uncertain about. We don't want to expose to other people. We have this concept of a core package, which is kind of quite widely adopted. So you could maybe stick internals under that, or maybe on the same side of it. And then core can be like your small surface area they're exporting out. So other things that are going on with the namespace aliasing, I've noticed that it's probably a better, like we kind of use this virtual method naming aliasing, which is what this Jesus and Necromancer thing is like. They're both raising the dead, but they're doing it in very different circumstances, Clojure. It might be better to add a namespace to say there's some separation between those two guys, okay? And I think we've also seen some problems with what I call the stupid suffix on a function. I called my function cat. There may be other cats. So now my function is cat star star degree degree. No clashes, great. But I've solved that for you, Clojure. You can take your stupid suffix and make it into a namespace, and it's solved. And Clojure, you're welcome. Okay, a question about state. Okay, I think at this point we can actually pat ourselves on the back. I think we can. No? It was easier to touch someone else than yourself? Okay. So where does state really belong? Okay, I think it was quite conventional when in the early libraries to always have earmuffs in the namespace. The global state that you're going to mutate because it made the rest of the code easier. And I don't think we see that now. So well done. Is the state in the with wrapper? Where we initialize some stuff and we have a macro or a function, wrapper function that returns stuff. My view is that that's not really where we should have the state. I think people have expressed it better than me already here. With wrappers or macros are hiding what we're actually doing, and we're not letting it exposed. So it's like a convenience, but it's really restricting what we can do with libraries when other people want to come and expand and use them. So my personal feeling is mutable state. Basically, def should only be declared in NSUser or def in main. And yeah, nowhere else. So I should initialize the library, or I should create some state, and then I should pass it to a function that's going to use that state. And quick question, Clojure. Should that state be passed in on the left or the right? Clues in the name, Clojure? Right, yes, it's on the right. Both because it's right and I say so. Okay. Next thing is exceptions suck, right? This is controversial even in OO code. I came across it recently with Clojure HTTP, which is a great library, but if you don't set some flags, then when you get a 404 error, a perfectly good error from a server that's explaining what's going on, you get a massive exception, right? You get stack trace blown, and your whole thing's gone. So I think instead of using exceptions, we need to simply do these things. We need to rethink all our programs so that they're repeatable cumulative operations only, make them nil tolerant, and we need to think about returning identity as being an acceptable solution to failure. I think Rich already mentioned this, but it's like there was an example in the talk yesterday of checking account balance, see if it's got sufficient credit to buy something. So if we have a person who wants to buy something and an item and an inventory, that's a very common real-world situation. And if we reject it because the customer doesn't have enough money, that's like a real-world shop, where we're all in a queue, and the person at the head of the queue goes like, oh, actually, I forgot my wallet. I can't pay for this thing. And the shopkeeper goes, stop, everyone stop, get out, stop the shop, we can't go on, we need to sort this out, we need to start again. That doesn't happen, right? Because it goes like, well, I haven't taken any money off you, you don't take the tin of soup, and the shop's okay, right? We're all okay. So, and the final thing is really that we need a robust logging framework for I/O and system failures where actually, we wanted to communicate something and we repeated a few times and we failed. I think other people talked about that on yesterday. So, now those are two very difficult things and two easy things. So if we reduce it, we have two medium things. Very simple. I think we can sort this out. A lot of people talk to me about mocking in Clojure. And they say it's very hard. And I say, really? Mocking Clojure is hard? Okay. So I think the issue is in OO, it's like this situation that I describe here, as we're mocking a cow so we can say what kind of milk it produces. We've got the kind of wrong granularity in OO code. We tend to replace a whole database connection just to say for example, what a select statement returns. So I've kind of invented this rule at the bottom of the slide. It might be too small. I put some code to illustrate it, but now my important thing you may not be able to see. So the basic rule is that if you think you need a mock, you can probably decompose your test into a unit test and a functional test, and you won't need a mocking. That's a rule, that's science. So I've proven that mocking isn't required in Clojure. Again, you are welcome, Clojure. Okay, so we've heard about the homoerotic properties of Clojure. We've heard it from Paul. We heard it earlier this afternoon. There's one place, though, that doesn't share this love. Build and deployment don't get no love. It's all XML and jars, okay, in build and deployment. We're still using Maven for our Clojure code. I think we need to take another look at that. So there's a recognition that development is actually decentralized. It's not like Maven Central goes like, yeah, let me check your developer badge. Yep, you can now create an open source project. But that's kind of the way it is with stuff like Clojars and some of the other repositories. There's a real restriction. We're developing stuff in a decentralized way on GitHub, and we're not kind of recognizing that in our build and deployment tools. There are some. If you look at something like Go install from the Go language, it's actually quite clever in putting together a URL, which becomes a package namespace, and pulling all that stuff down and installing it and compiling it locally. And I think you could do exactly the same thing, because actually Clojure projects have a really regular project structure. One thing that Leiningen's done is kind of said, this is what a Clojure project looks like. And so therefore, if we could specify a kind of GitHub branch that was a release, we could decentralize build and deployment of code, and Clojure could itself become the deployment user of Clojure rather than a jar, which is what it is now. Okay, so yeah, 1979 called me during the lunch break. It's quite confused. It thinks you're all programming mainframes. So I think we need to kind of clarify something here. Contrary to popular belief, Clojure variable names can be longer than 8 characters. It's not mandatory to put a number in each one. It's only acceptable to have your functions be F1, F2, F3 if you're writing something for motor racing. Okay? Cons and cons, they're not models to emulate. They're not aspirational. And there's a more serious point here that it's fun to have REPL code and develop things in an expression-driven way, and it's not fun to maintain someone else's REPL. Okay, so I think we need to have a little mercy on other people here. Okay, and more generally, let's just stop doing stuff. If the first rule of Macro Club is don't write macros, why does every library have a wrapper macro? Okay, and when you need to write a talk quickly, why isn't there a def talk? It's pointless. So I feel like things like macros and protocols and records, you shouldn't use them, Clojure. They should use you. You should be crying out for them before you use them. It shouldn't be the case of like, well, I wrote this cool library. It uses like a macro that defines like a protocol, and then it has a def record that implements the protocol, and you probably wouldn't get it, so it's not for you. It's, these things have real use cases. It's not like going through the Gang of Four book and implementing every pattern in your code base, although that was fun as well, okay?
Okay, so I'm going to talk to you about a thing called Riemann. It's named after some maths dude. You may have seen some early tweets I may have done where Riemann was spelt differently because it was named differently, and then it got renamed and the I and the E switched places, and my dyslexia kicked in big style and I got really confused for about a month. I didn't write it, but I have used it and it's kind of fun. So there's a whole class. I work for ThoughtWorks. We're hiring. We're always hiring. Anyway, I'm here to talk about the C10K problem, although I'm not really. So the C10K problem is like a class of problems for web servers. And it's this idea that for some reason we need 10,000 concurrent connections, because at that point we get a Y Combinator investment and or something like that. I think that's what happens when you get to 10,001. But there is this legitimate issue where we can't handle many concurrent connections, And there's a whole lot of servers out there that claim to have solved this, like Nginx. So Nginx is written by a mad Russian, and therefore it's awesome. And Tornado, which is Python, and therefore it's kind of okay. And then there's Node, which is really confusing. And then there's Netty, which is what I want to talk to you about, although not really. And they're all about trying to break this connection between a connection and is a thread, right? Because if you have 10,000 threads on a box, it kind of sucks, right? Because you spend all of your resources of your machine time dealing with CPU and just swapping threads around, and that kind of, it's not much fun. So a lot of what these servers are doing is breaking this connection. They're saying, I've said connection a lot, thing. They're breaking this thing down, and they're making it all evented and asynchronous, and there's event handling and stuff going on. Not really important, actually. This is Netty. It used to be part of JBoss, now it isn't. And they've got a 0-copy capable rich byte buffer at the bottom. Don't know what that is. There's HTTP. I know HTTP. Basically, it's just like a server that can handle lots of connections, and you can build things on it, like a web server or a mail server or whatever else. And anyway, this guy's basically taken it and built a streaming event-based server on top of it. Anyway, Netty runs on the JVM and it handles, that's all you really need to know. Now this is Riemann, and Riemann is a Clojure server built on top of a Netty. And what it does is it monitors distributed systems. Well, it doesn't really monitor distributed systems. What it really does is it receives streams of events and then lets you apply filtering and transformation and roll-up metrics and forwarding on those streams to data sources or graphite or things like that. It happens to have been implemented with monitoring in mind, but you can kind of use it for anything. And that's where you can find it. Search for Riemann with the I before the E. And so this is the classic case of where it gets used. You've got loads of clients, these might be servers, and things are happening. CPUs are going up, CPUs are going down. Stock market's going up. No, it's not, it's going down. And all of this data is useful information, and it's operational stuff, there's disk usage, I/O, there's things like how many orders you've placed, how many shoes. Don't know why I'm looking at Rob when I say those shoes, and I'm sending this information, and it's floods of information, and there's a lot of things going on there, and I want to know what's going on. So Riemann basically collates all of this information and does stuff with it. It's got an index that gives you a little dashboard of what's happening kind of right now, and then you forward things off to Graphite and wherever else you want. So we're going to run through some really simple examples that I've copied from the website, so I kind of hope they work. But what they send are these things called events. Everything's sent over protobufers, over either TCP or UDP. If you don't know what protobufs are, they're kind of like Corba, but Google did them, so therefore they're cool. But it's a lightweight binary protocol. You have a shared little definition of what they look like, and you can unpack them. There's language support for lots of things. They were designed to be lean and have fairly good version compatibility. And so everything you send, in terms of what Riemann can receive, you need to know where it's come from, the service, the state, which is more just a level of seriousness, bit of description, and you get tags and metrics. It's a very, very simple standard protocol. And you can do things like this. So I can say I want to work out my percentage of maybe the number of API requests I've had. So this works out the sort of running percentiles on a given metric. So the 5 means every 5 seconds, calculate the 50th, 95th, and 99th percentile. Index is just a function, but it's actually in this case being used as a destination. So in this sense, index means update the local running view of my world, my Riemann world, with the result of that percentile. I could just as easily send that information to a different place, and we'll see that next. Let's imagine all these bad things are happening, and I need to email where's Kush? I need to email Kush and tell him to get up and go fix something because the world's falling down. So I want to go eek and send an email. Well, Riemann can do that too. So here we are. This is using a roll-up function. So firstly, I define a destination. There's a function here, tell ops. So when I get a message of state critical, tell ops, but ops is doing a roll-up. So this function basically means that it'll only send a maximum of 5 emails every hour, collating all of the results of the disaster situation. So I can now do events without being spammed via my email. What about if I want graphs? Graphs are cool, right? You know, this is these are graphs. So how do I send information to graphs? Well, that's really simple too. So again, another destination. This is built-in support for Graphite. I specify where my node is. Graphite is a Python-based system. It's kind of got three parts. It's got a round-robin database, which stores data. It's got a little receiver that receives information in the form of pickle, and it's got an interface for creating these graphs. It's very cool systems. It's all built in. So in this example, you're seeing the stream matching. So again, here I'm saying anything from my web request service, I'm going to group these things by host, and this rate1 graph is basically a way of looking at a given value of a metric divided by time. Here I'm graphing hits, so it doesn't really make sense for it to be any other value. This will tell me how many hits I've got, and I'm sort of aggregating these stats, splitting it out and forwarding it on. What if I want to do something really funky? There was a talk, I think it was a Clojure conj, last year, talking about logs of data, logs as data, this idea of, you know, having sort of events forwarded and aggregated on and stored and all this kind of stuff. So what if I've got thousands of machines? I've got like lots of different data centers. What if actually I've got so much information that I need to, in some places, throw it away, in some places, forward it on and aggregate it? So maybe what I want to do is collect all my events, store them in Riemann, drop some stuff, aggregate up and forward on. That's great, that's 3 lines of code there. So this situation says, okay, I'm going to define a destination, and whenever a state changes, I'm going to forward it on to some destination, which is another Riemann client. Now, of course, at this point, I could filter out things at a certain level. I could apply roll-ups or aggregation. So I can take vast streams of events and filter and filter and filter it down, and then I can actually drill down to get the low-level clarity I need by going back to those precursor nodes, and that's all very, very cool and fun. What about free beer? Yes, free beer would be great, thanks. Doesn't do any of that stuff. Why not just use Graphite? Graphite does do things like just take data over things like UDP. The problem is the data is too much. If you think about operational data, things like CPU memory, if you're pulling that information from SAR, it's already aggregated. You're already getting samples, say, every 5, 10, 15 seconds. If you're monitoring Amazon boxes, it might only be every minute. When you're pulling back data from your applications, it's not pre-aggregated. You know, the number of orders I've got, the volume of data is often just too much. So Riemann is fantastic for filtering out this information beforehand, and it can do more than that. You know, I can take some stuff, send it off to Graphite, stick the rest in a cube for analytics data. I can pre-aggregate, do all that kind of fun stuff. Is it production ready? The guy that created this is using it in production at Show You. He's using it for handling, you know, he can handle... Does it not work at Show You? He works at Boundary, that's very true. He's using it there, and he's using it for large numbers of events in production. There's a couple of people I know that are also using it in production, but it's very, very cool. And it's fun. And this is a real world, I think the thing that's interesting for me is this is something I can sneak into an operations department, and I won't ever have to mention its Clojure. And it's something interesting that happens when we have these new languages that come out, is that, you know, everyone goes out and writes a mocking framework or a unit testing library. People don't go and build things that we can actually use. And at a certain point, right, no one actually cares what Postgres was written in. It's probably written in C, it just works. People need to build things that kind of just work and are useful, because when we want to talk about how great our language is, it'll be great. So, you know Raymond's written in Clojure, right? That's what we should be doing. And so this is very cool, and you should go use it. Thank you.
All right, so HTTP asynchronous client is a library based on asynchronous HTTP client, just to confuse everyone with the names. Yeah, it's a good library. So let's load it up. First the namespace. I have a server already prepared before, so we don't have to wait for starting it up now. Okay. And so I loaded already all the libraries. I hope, did I? Yeah. So now I created the client. It's readable, right? For at the end as well. So customized with user agent. There is a bunch of other options. No, you cannot really read it. Okay, so I'll try to, you won't see the beginning of it, I don't know why. So there is, client can be customized with follow redirects, compression, keep alive, maximum connections, and some other stuff like authentication, proxy. That's coming for free. So let's issue a simple request. Now, once we have that request, let's see what it really is. No, we won't see it here. Or maybe we will. So, okay, request is actually a map of promises. Most of the stuff is promises. So there's a promise for status line, there's a promise for headers, there's a promise for body, for error, for being done. Those are internally getting delivered by callbacks, but that will be covered a bit later. So first, let's await for a response. It's asynchronous. So when I issued that call, you didn't have to wait. We didn't wait for it. So first we will await for it, then read the status and pretty print it, which probably you won't really see. Yeah, you will see some of it. So there is a status code 302. So yeah, it's a redirect. In case it would be 404, it would not throw an exception at you. When we investigate the headers, see the location is there, nice. There are some convenience methods to actually investigate whether it is a redirect and what's the location. Now, okay, so now I will create a redirecting client. That's another customization for a client that will just follow redirects. Simple same request. Okay, this time. Okay, now you would see it normally. Presentation is on GitHub, maybe. Yeah. Did it really help? Not much, did it? Yeah, you can see some here. So we can, but you won't see the code here. It's quite straightforward. The response of the body that is returned by the HTTP client is a byte array output stream. So you can do the standard IO Java stuff on it. So saving file is very straightforward. So that's file saved to info.json, and it will be here. Not that one. Yeah, that one. So yeah, that just saved it. Not very useful, right? But still, some people ask for it. So now we can investigate the content type without actually going through all the headers. Yeah, we can take a string representation of it and parse it and pretty print it. So all nice. And we can also, no, we should actually close the client at the end. It's asynchronous, it has quite some threads running. So if you leave that client running, you won't get your JVM stopped. Now, there is a bit more to the request than just URL. Here's just an example of query. The service returned what we passed to it and said something, some more. On a request level, you can provide headers, different forms of body, cookies, proxy, authentication, timeouts. Now, there is a kind of, oh, we won't see the whole of it. So there is a specialized form, create sequence, a stream sequence, that's for requests that you know that, or you don't expect that they are going to finish or are too big that you wouldn't like to store them all in memory. So we will get the lazy seek backed by a linked blocking queue, kind of like CQ from Clojure core. So what's going to happen here is request a resource that will produce a stream. Then we will take the stream, we will run the string representation. We will try to get a string representation of it twice. Then within two futures, we will consume them. Each of them first will print the first element and then consume the whole sequence, just to show that it's not broken in case of like that consuming the first element already takes it out of the queue. So it is still compliant with with a sequence abstraction. So I don't know what we'll see. Yeah. Okay, so you see that they are interleaved. Each got different message. They didn't do any real error here. So, okay. Now for callbacks. No, that's not yet callbacks. That's request stream is a specialized function that just takes the body part callback. So whenever you receive a chunk of a response, you get called here with that callback. First parameter is request, then there is a part, which is again byte array output stream, so you can do standard Java stuff on it or concatenate to collect all the response. So we're gonna take the string, parse it, print it, and each callback has to return a body part callback has to return a tuple, the same as status callback and headers callback. First part is what is going to be delivered to a promise within a response. So you don't need, it can be managed automatically. You can manage it yourself by delivering something different here. Second part is actually whether to continue or abort. So you can abort the request processing even after receiving just a status line. You don't have to actually consume the whole thing. So here again, we're printing nicely. It's just working. Now, that's a full version of callback interface. So it's actually most popular throughout the libraries that use this library. The callback interface, I think for automation is probably the easiest. So what we are going to do here is actually deliver, first part we are going to deliver to the body promise of a map, and then we are going append to it whenever we receive the next part. At the same time printing all of the stuff that we're receiving. And at the end, we are going to take the string representation of it and just say what was it. So that's it. Yeah, we have, there is a status line callback, headers, body part, body complete, and an error. So you should not really see exceptions when you call that stuff. You should get them in a promise. That was the idea. Okay, that just shows that you can actually deliver whatever you like to the body part. Here we will deliver just a keyword, and on completed we will just print it. Okay, so the body contained now only test. Now that will show actually that you can abort. So the first part that we are going to receive, we are going to print it, deliver the part that we received, abort the further processing, and on completion we will print whatever was in the body. So that worked as expected. And okay, this is a bit more complex. We are going to use here a counter to count the body parts. We are now within a body part callback. We are going to deliver that counter, count it, and at the end we are going to, when it is completed, print the value of the atom from the promise. That's why things look like that. Yeah. Okay, this is actually, this is closing over a counter and using a standard callback from HTTP asynchronous client that is collecting the body, so we don't store it in a body, the counter. No, we received a good amount of everything, that's nice, and so okay, this is to show simultaneous execution of the same request. So we have only one request prepared. If you would like to add additional stuff, that's where we would add it, like the query parameters, header, whatever have you. Then we are going to execute 7 requests. 7 times those requests, delivering to body only the ordered number. I hope they will actually show it. Oh yeah, see that's actually shows that they all returned asynchronously. And that's something that is in the making now. WebSocket support. For now, it is barely callbacks. Callbacks and send method, a send function that you can actually, so this thing will return the WebSocket, the whole, this will return a WebSocket that you can do this kind of stuff on. The same socket that you are getting in a callbacks. There is a callback for text and bytes for some binary protocols over WebSocket. So what is going to happen here, we are going to talk to Echo server, Echo WebSocket server. Whenever we receive something, we will print it. Then on a first message, on the welcome message, we will spawn two futures. First one will print seven messages to the server. We'll send 7 messages to the server. Other will wait 100 milliseconds and be done. So yeah, we can see. Yeah, we can see that it's actually asynchronous. It's full duplex communication, and that's pretty much it for the walkthrough of it. It's very lightweight library, so give it a try, and that's it.
Okay, so this is Western music notation, which is a domain-specific language for representing melody. It doesn't, I've got a slight bit of cut off there, but it doesn't really represent any high-level concepts. It's a graph where the x-axis is time and the vertical axis is pitch. And so concepts like chords and repeats and things like that aren't really directly represented in the language itself. And so that's what Western musicians use to write down their music. But what that means is that when composers have higher level concepts that they've put into their composition, these are missing from the finished product itself. And you could see that it's a regular language, or you may or may not be able to see it, which means it's like the kind of language that a regular expression can recognize. And there's a good reason for that, because just like Clojure is hosted on the Java virtual machine and is constrained and informed by that, Western music notation is also a hosted language. It's designed to be executed on a rather peculiar kind of finite state machine called a musician. So the cognitive load of processing kind of nested definitions isn't really reasonable for a person who's reading that and performing it in real time. But if we're using code to compose and to perform, then that's not really a problem. And so I'm going to go through and show how to represent that same canon in Clojure, which you'll hear at the end. Just first, just do a quick sound check. You can find the sound jack. Hear that? No. Is there anything that needs to be done to switch the sound up? Mine's on. Oh, there we go. Did you see something? Hear something, maybe? Is that quite audible? Cool, thank you. All right, well there's a basic piano sound. So I'm going to use Overtone to drive this, but most of the stuff that we're going to cover is going to be built from scratch. So from Overtone we're borrowing the concepts of at, now, and hopefully we won't need it, stop. And rather than build up a synth, because that's Sam and Jeff have already covered that, we're going to just deal with sampled piano sound. And so when we looked at the Western music notation as a graph, another way of looking at it is a sequence of pitch time pairs. And so we can just write a function that will play a series of tuples that are time in milliseconds and pitch in MIDI. I'm just going to demonstrate that by playing the MIDI notes from 60 through 72 and giving them time values that will evenly space them out. So that sounds kind of musical, but also a little bit weird. And the reason it sounds weird is that we haven't made use of one of the basic concepts in music, which is scale. So in a piece of music, it doesn't typically play every note, like we just did then. It sticks to a specific subset of those notes. And which ones are in the subset and which ones are out are defined by a pattern of big and small jumps between the notes. So in a major scale, which you may have heard of, even if you're not a musician, the difference between the first and the second note is a double jump. The difference between the second and the third is another double jump. And there's a single jump, double, 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 single. A minor scale is very similar, but the jumps are in a different configuration. And so we can very easily write a function that'll tell us, if we give it where in the scale we are, what the actual pitch it is, taking advantage of these big and small jumps. And if we want to not use an abstract major scale, but actually make it G major or G minor, all we need to do is compose that function with another function that offsets from the base of our scale. I know that's kind of a bit of a mouthful, but I'm just going to play a little bit of a melody that is using D major. And then I'm going to play it again in minor, so you can hear the different emotional effect you get from differing these patterns of big and small jumps between the notes. All right, so that's the first couple of bars of Frere Jacques, now in minor. So you can see there's a very specific mathematical difference we've made, but it's actually got quite an artistic and emotional impact. But scale is an abstraction that almost every piece of Western music at least respects, maybe ignoring some of the modern stuff in the 20th century. But you also have the ability to create abstractions that are specific to the genre and the piece that you're after. So in Bach, there are a lot of series of notes that are adjacent, and they go up and down and wander around the scale. So if you were trying to write a piece of Bach music, the way to make the structure of the music more obvious, more evident perhaps, is to use a run function, which I've defined here. And so with a run, you get a bunch of notes that are next to each other, and you'll hear a lot of things like this in Bach's music. So there's a whole lot of notes that are next to each other, running along, going up and down. Now, you can use those to build the melody itself. So you don't need to appreciate every detail that we've got on this piece of code. But you can see that I'm taking advantage of the fact that there are runs within the music, that there are repeated notes of the same duration, that there are 3 logical sections to it that I can then concatenate together, that the bass has a lot of sections with 3 notes in a row. And so this is not something that you could represent in Western music notation, where you have to actually write down every single note. We're being a bit indirect here, so we can write down what the composer meant rather than the resulting rendered notes. But at the end of it, just like with Western music notation, we have a sequence of tuples of time and pitch. So here's where we get to the specific canonical bit. A canon, which can be defined very easily in English and Clojure in about the same length, is a melody that is accompanied by a functional transformation of itself. So it really is a very functional concept. So here we have, you can read it in Clojure, and it's almost exactly the same as how I said it in English. So if we want to define different kinds of canons, which are defined by different kinds of transformations, remembering that our tuples have timing as the first element and pitch as the second, we can just define transformation functions. So a simple canon is one where the second version of the melody is delayed by a fixed interval. And you may have heard people talk about row, row, row your boat this way. So in a classroom, children will often sing it with one group of children starting off and then the second joining in after a fixed interval. And because row, row, row your boat is composed to be a simple canon, that sounds musical. An interval canon is a very similar concept, but the shift happens in pitch rather than time. So we just offset the different half of the tuple. A mirror canon is slightly more interesting, and we're using negation to negate all the pitches. So what that means is the accompanying melody is flipped vertically, or around the x-axis if you were to think about it as a graph. A crab canon, so named because in the Baroque period they thought crabs walked backwards, is one where you apply negation to time. And obviously, these are all very functional concepts, so it shouldn't be surprising that Baroque composers also used functional composition. A table canon is one that is a composition of a mirror and a crab canon. So it's flipped around the x and the y axis. And the reason it's called that is if you imagine that piece of music sitting on a table between two musicians, the guy or girl who's seeing it upside down is actually seeing it reversed in pitch and time, hence the table canon. But if we don't want to have to use physical wooden infrastructure, we can actually use functions in Clojure. Now, the specific canon that I'm talking to you today about is by Johann Sebastian Bach and called Canoni alla quarta. And we can apply the canon function, i.e. accompany itself. And we give it the transformation of dropping the melody, of flipping the melody, and by delaying the melody. So these three things together come to define the transformation of the canon function. Now, what I want you to try to appreciate is it's not just a case of taking any old melody and messing about with it. To compose a melody that actually sounds really musical when you do this to it, it takes an incredible amount of skill. And I like to think of it a lot like programming, actually, where you can take a really austere and formal framework, but by applying human creativity to it, it can end up with a really beautiful result. So I'm going to play you the introduction to Canoni alla quarta, and then I'm going to mess with it slightly and play it again. Oops. So those are the actual notes that are being played, that are also being spat out for Clojure. But since we're live coding and we can mess around with things if we want, we can also change the key and change the pace slightly. So what this does is just give different inputs to the functions we've used to define the key, the big and small jumps, and the function we use to work out at what time the various notes happen. So this will be the end of the tour. Thanks very much.